let's start with an example 5.1 of this chapter 5. Okay, that is a best example and detailed example for the design of shear. Okay, in the beams, a simply supported rectangular beam of size 300 by 525 millimeter, that is a rectangular section, having an effective depth of 450 millimeter. We got this section after designing in the bending against the bending moment. Okay, now we are going to check for the shear force. Carries a total factor load of 130 kilonewton per meter, that is a factor load. No need to apply the factor, already factor load. The clear span of the beam is 4.5 meter. Okay, the effective span, that is a 4.8 meter. Why? That is shown in the figure. Okay, I will when I explain this example statement, then I will go in the figure. The flexural reinforcement consists of, after designing against the bending moment, that is 8 number 25 bar. The diameter of 125 diameter of number 25, that is 25 millimeter, and the area of in the SI system, that is 510 millimeter square. So 8 number 25, that will be 4080 millimeter square. 1 bar area 510 millimeter square, then the 8 bar will be 4080 millimeter square, and the 4 bars of which are curtailed and 4 are continuous. Okay, as you know, when the bending moment at the spots is minimum, and we can curtail the bars. In this example, use concrete grade 20 and steel grade 280 megapascal. Using double leg stirrups, design the web reinforcement. Double leg, when you have seen, I'm sure what is double leg. Okay, here you see this section, rectangular section, one leg of shear, the second leg of shear. Okay, and that is one leg. Here 1 2 3 4 leg. Okay, that is the 4 leg section. Now I will again go back to the problem statement, example statement. Here, using double legged stirrups, design the web reinforcement. Means design the stirrups for this example using double leg stirrups. Okay, the first of all, here is the applied load is given, factor load. We will draw the shear force and bending moment diagram. Okay, here that is the shear force and bending moment diagram. The clear span, that is 4.5 meter, and the effective span means center of support to the center of the support, that is 4.8 meter. Why 4.8 meter? The support that are 300 millimeter, so half, that will be 0.15 meter, 0.15 meter from one side, from other side. The total effective span will be 4.8 meter. Okay, so after here the shear force and the bending moment diagram is drawn. Okay, so for the design of shear, we have to calculate the shear force at location D. Means from the face of the support, to the location at distance D, we will calculate the applied shear, and also we calculate the applied moment. So first of all, we will draw the general shear value for the whole section. Similarly, mx for the whole section. Then we will put the distance D only from the face of the supports, 0.15 meter plus D. Then we get automatically from the face of the support applied shear and the applied moment. Okay, so how I will calculate the applied shear and applied moment in the form of Vx. That is again in many problems and many examples we have discussed and we have also performed in the previous classes, like in structural mechanics. Okay, so here the same beam. Okay, the same beam, the effective span length is 4.8 meter, and the load, the factor load, that is 130 kilonewton per meter. The half load will be on the as a reaction on the left side, and half load will be on the right side. That will be omega L by 2. Omega L by 2. Omega is 130 and span length is 4.8 meter. You will get the answer 312 kilonewton as a reaction for the right, and similarly to 312 kilonewton for the left side. Okay, and when we cut this section, here is a notation symbol. Okay, here I have put the journal and cut this section at a distance x from the right spot. Okay, here you can see 130 kilonewton per meter, 312 kilonewton, and distance x, vx, and mx, that are symbols. Okay, here upward force Vx plus, and this one is also upward 312 plus, and 130 kilonewton loading acting downward, so that's why minus 130 into x, that is UDL, so that's why multiplied with x minus 130, and when you will simplify, you will get the answer Vx is equal to 130x minus 312. Okay, now for the moment, you will take the moment at that point by these all forces mx, that is moving clockwise, that is mx minus mx. At this point 312 is revolving anti-clockwise, that is 312 into x. Okay, then this one 130, that is acting clockwise, so that's why minus. Okay, 130 into x, that will become load at the center, and for the lever arm you will multiply with x by 2, and then you will close the equation equal to 0. By simplifying, you will get the answer mx is equal to 312x minus 6.5x square. Okay, 312x minus 6.5x square. Now I will again go back here. The author calculated the Vx 312 minus 130x and mx 312x minus 65x square. Mx we got the same, 312x minus 65x square, but there is minus issue in the Vx, that is 312 minus 130x. Why? Because author have used the symbol differently. In the Vx, that is used downward arrow, then you will get the same as that of author. Okay, so I have used the same principle that we use in the previous semester classes, so that's why I got the answer 130x minus 312. When you will draw the shear force diagram, you will get the same answers here. Why this answer is much better and the good, will you give the good result? Okay, when you will put the value, then you will get the value in the negative. Okay, so here you can see from this end to this end, that is positive shear, from this end to the right, that is a negative shear, and here when you will put the value, you will get the negative shear. Okay, but when we go for designing of shear, it does not matter what is the value, either the value is in the negative or in the positive. We have to get the absolute value, and then we go for the design. So that's why it will not matter, either by this equation you will get the shear, and either by this equation the answer will be the same, no issue will be there. Now first of all, I will calculate the shear capacity. Okay, shear capacity formula is shear strength formula for the concrete, that is VC equal to 0.16 lambda. Lambda is lightweight coefficient for the concrete. If you are using a normal weight concrete, the gamma will be 1, and if you are using a lightweight or the heavyweight aggregate, this lambda value will be changed. Then multiply with under root fc prime concrete strength plus 17 into rho w. Rho w is the steel ratio. In your in this section, the steel ratio that is 8 number 25 bars, you will divide the total area 4080 millimeter square divided by BD. Then you will get the rho W, and then you will multiply with VU D MU into BWD less than equal to 0.29 lambda under root FC prime BWD. All the parameters are known. I will put one by one. Lambda is 1 because normal weight concrete. Under root FC prime 20 megapascal plus 17. Rho W, that is 0.015 VU, that is applied shear, 234 kilonewton, where this VU and MU is calculated at distance D from the inner support. Okay, from this support, this inner edge at a distance D, we got the values of VU and MU. Okay, when you will put the values at X, 0.15 plus 0.46, total 0.6 meter. When you will put the values 0.6 meter in the Vx formula and in the Mx formula, you will get at a distance D, VU 234 kilonewton and MU 163.8 kilonewton. Remember one point, rho W is half. Why? Because in the question statement there is mentioned that the 4 bars are curtailed and 4 at the face of support. Okay, when the 8 bars entering into the support, the 4 bars are curtailed, so that's why at the support the steel ratio will be less, that is 4080 by 2 means 4 bars are curtailed, total are 8 bars, so that's why divided by 2. Okay, the answer of rho W, that is 0.015. So that's why 0.015 VU D divided by MU. VU is applied shear, D is effective depth, MU is the moment. The value is 0.643 you will put, and you will get here as it is BW, that is the beam, that is 300, and the effective depth that is 450 divided by 1000. Okay, to convert into kilonewton, similarly 0.29 1 under root FC prime 300 450 divided by 1000, you got the answer. Same in the equation like less than or equal. Our answer is of concrete shear strength, that is 118.7 kilonewton, less than and equal to 175.1 kilonewton, that is okay. So we will pick the VC value, means concrete shear strength value, that is 118.7. Now we will multiply the concrete shear strength with the factor, that is 0.75. Then we will get the value concrete shear strength capacity. Okay, design shear strength, okay, of this beam, that is 0.75 into 118.7, that we have calculated the concrete capacity. The answer is 89.03, and then we divide this capacity by 2 because that is ACI requirement. We check the applied shear by dividing the concrete capacity by 2. Okay, so our applied shear value at a distance D, that is 234 kilonewton. Applied shear is much more than the concrete shear capacity and the concrete shear strength. Okay, means applied shear is much more than the capacity of the concrete. Transverse reinforcement is required, means ties or stirrups must be provided. Okay, so here VU, that is applied shear capacity, is 89.03. so total applied shear, this will be resisted by the concrete capacity. Okay, then 234 minus 89.03, 144.97, means this much applied shear must be resisted by steel. Okay, this 89 will be resisted by concrete, and the remaining from 234 minus 89, 144.97, means you have to provide the steel in the form of ties or in the form of web reinforcement to resist the applied shear. Okay, here now this we will get 144.97. Okay, that will be equal to 5 Vs. Then here Vu minus 5 VC divided by 5V. Okay, if you take 5 on the other side, that will become 5 Vs. And why calculating Vs? Because to check the conditions. Okay, is it our section depth is okay for the design of shear? So that's why we are calculating the Vs. Vs Vu minus Vs means the steel required in this section to resist the applied shear. How much? 144.97. 144.97 divided by 0.75. So answer is 193.3 kilonewton. Okay, so here is a check. 0.33 under root FC prime BWD. The answer is 199.2. Our Vs, if you multiply this value with 2, you will get 0.66 under root FC prime BWD. In the previous discussion, I have discussed if our Vs is less than or equal to 0.66 under root FC prime, okay, that is 199. If you multiply with 2, that will become 400. Our Vs is less than 400, so our cross-sectional dimensions are okay. And if our Vs is greater than this 0.66, then we need to revise our section, means we have to increase our section depth. And again our Vs is less than 0.33, then we will follow the conditions for the spacing. Okay, here some mistake. Vs is less than 0.33, 193 is less than 199, and now we will follow the spacing criteria accordingly. Let's take the diameter of the bar number 10. Okay, the area of the number 10 bar, that is 71 millimeter square. So that is a 2 leg. Okay, in the cross section there are 2 legs. Okay, when we provide the tie, okay, to resist the diagonal cracks, okay, so there are 2 legs, 1 leg and 2 legs. So that's why the area of 1 bar of number 10, that is 71 millimeter square. So in the one stirrup there are 2 legs which will resist the applied shear. That's why multiply with 2, 71 multiply by 2, you will get the area of the leg, that's double leg, that will be 142 millimeter square. So S max will be smallest of the following 4. AV FY 0.35 BW. I will discuss detail. AV is the area of ties, legs, tie legs 1 and 2, and if there are 3 leg ties, okay, then you will multiply with 3 times 71 millimeter square. In this case we are using 2 leg, so that's why I multiply with 2. AV is 142 millimeter. FY, the grade of our steel, that is 280. Down in the denominator, that is 0.35 into 300. So we got the answer 379 millimeter. Second criteria is D by 2, that is 450 divided by 2. Effective depth divided by 2, that is 225 millimeter. Third one, that is general criteria given by this author, not by the code, that is general minimum 300 millimeter. And the fourth criteria, that is 5V AV FYD divided by VU minus 5VC. Our VU minus 5VC, that is 144.97, and on the upper side, that is 0.75. AV 142, grade of steel 280, and effective depth, that is 450. We got the 92. Now the minimum of all, that is 92. Okay, so for safer side we reduce 2 millimeter. So let's provide the spacing at 90 millimeter center to center. Provide number 10 bar at the spacing 90 millimeter, that will be okay. So our spacing should be greater or equal to 80 millimeter, that check is also okay. Now for the providing of stirrup, we provide the first tie at a distance S by 2. Okay, what it means, I will come back at 0.9. okay, Now I will go in the diagram. Number 10 at 90 millimeter center to center. Here is the spot. The first stirrup or tie will be provided at a distance s by 2. Our s is 90 millimeter. 90 divided by 2, that will be 45 millimeter. Means first tie, this tie, okay, this tie stirrup you will provide at a distance 45 millimeter first, second, third, fourth, fifth, similarly. Okay, number 10 at 90 millimeter. I will explain later what are these. Okay, first of all, I have explained is in this small topic that the first stirrup should be provided at s by 2. Our s is 90 millimeter divided by 2, that will be 45 millimeter. Now when we will see the shear force and bending moment diagram, there is one point, okay, and there here is the shear force. Now you see shear force is maximum at this spot, but it start reducing when it go to the midway of the beam. So we can reduce the area of steel or reduce the number of ties at the center. And why? Because shear at the center is minimum. So again, this author provided a guideline. You can reduce the number of ties at a location ln by 5, okay, here, or ln by 4. First stirrup, that is number 10 at 90 millimeter, is provided at s by 2. First stirrup is placed at s by 2, 45 millimeter distance from face of sport. Now at which location we can reduce the area of ties, okay, or the number of stirrups, that is location ln by 5 and ln by 4. ln by 5, that is clear spacing. Our clear spacing, that is 4500 millimeter divided by 5, answer is 900 millimeter. And ln by 4, author have given the option, you can choose either ln by 5 and ln by 4. Okay, now I will again calculate the shear force at a location ln by 5. Okay, here when you take the ln 4.5 meter, that is 4500 millimeter divided by 5 at a 900 millimeter from the face of sport, I will again calculate the shear force and bending moment. Then at this section I will again calculate the capacity of this section. And now at this location into the inward, okay, in this region there is minimum shear. I will provide a minimum number of stirrups, okay, for that at ln by 5, okay, here 11 intervals of stirrups may be provided at a spacing of 90 millimeter. 900 divided by 90, okay, you can calculate simply 900 divided by 90, okay, 10 stirrups, then the spacing will be 11. 11 intervals of stirrups may be provided at a spacing of 90 millimeter. The location of last stirrup is defined as why that is 11. Okay, the first stirrup will be at this location 1, okay, then 90 millimeter second, at the end there will be 11th. Okay, now to calculate the location at the ln by 5, so x, that will be location 0.15 plus 0.045, that is s by 2, plus 10 times 0.090, means 90 millimeter spacing. I will again go back in the figure, okay, here you can also take from the right, that will be 0.15 meter, okay, that is half of the sport. And then the first stirrup, that is s by 2, and from the first stirrup you have provided the 10 ties, at 90 millimeter spacing. So that's why that is 0.15 plus 0.045 plus 10 into 0.090. So your X location will be where you can reduce the number of ties 1.095 meter. Again, I will calculate the applied shear and moment at this location. The same formula Vx and Mx that I have derived already here. Vx formula and Mx formula you will calculate again applied shear and moment at this location. Okay, applied shear and moment at this location. Now again in the concrete capacity formula, Vu is 169 and Mu 234. You will get the value of this, and rho W here that will be 0.030. Why that is 2 times? Because bars are curtailed at this port, but away from this port there are 8 bars, so that's why 0.030 steel ratio. The same formula, only the difference is 0.030 and less than or equal to, again that is same. Okay, so Vc is in this after a distance of 1.095. Your concrete capacity is 119.04 kilonewton, again less than 175. Okay, again calculate the design shear strength, multiply with factor 0.75. okay, divide by 2 to check. Now your applied shear is 169, previously that is 234. okay, shear is reduced, so 169 again is greater than the concrete capacity. okay, your again applied shear is greater than the concrete capacity, means transfer reinforcement is needed. Now S max, the smallest of the following. okay, here is the 4 criteria. These formulas I have already discussed. So first answer is 379, second is 225, third 600 millimeter, that is again given by the author in general. The fourth one, these 3 criterias are given in the code, first, second and third. This 306 millimeter are is given by this author. okay, so where shear is minimum, no need, so this criteria is more, this spacing criteria is more. So the minimum of all the 4, that is 167 millimeter. It is rounded to 160 millimeter, we can say 160 millimeter. What it means now, from onward, okay, for at the start we have provided 10 stirrups now of number 10 at 90 millimeter center to center. Here that is number 10 at 160 millimeter center to center. How this 7 number of stirrups are calculated? Here are 10, and how 7 are calculated? First of all, the location is calculated where no tie reinforcement is needed. How we can calculate the location where no stirrups are needed? To find the location after which stirrups are not required, theoretically let Vx equal to, means the applied shear equal to half of the capacity. So here is the concrete capacity formula, that is simplified formula, approximate relation. Vx 312 minus 130x equal to 0.75 divided by 2, capacity divided by 2 into 0.17 under root fc prime bwd. You got after simplification you get the location of x where you do not need any stirrups. okay, so x 2.1 meter from this face of support, 2.1 meter. After 2.1 meter at the middle there is no need of tie reinforcement. That's how that is calculated in this section where no stirrups are required. But as a safety or the that is theoretically, but we at least must provide this minimum spacing. Okay, so here continue a spacing of 150 millimeter for 7 intervals, means for the in this section that will be first in the 900 millimeter, that will be at 90 millimeter, at this section 160 millimeter, and in the remaining you will provide at 150 millimeter center to center. So that's how we provide the stirrups in the beam against the applied shear. And here the top reinforcement, the bottom reinforcement is given from the in the design problem. Okay, we do not know how top and bottom is calculated. That is the question in the design of flexure against the bending. And in this example we have did only the calculation of this spacing and the diameter of tie. Okay, here the section is calculated in the region of 90 millimeter here. So that's why number 10 add 90 millimeter center to center. And most of the time there is dia of bar is written and not the number of ties. Okay, that is 7 and 10. For the dia written, the hash is written at the start. Number 10 add 90 millimeter center to center. So that's all for today's lecture. Have a nice day.